throughout all this process, you got M is 0.5 kilograms, 0.50 kilograms. Big L, the total length is that. I is 12 amps. B is 2 Tesla. Okay, there's a lot here. I do a lot in the notes there. I think it kind of goes around the same circle of what we've been talking about. Let's take this and really run the show. And just be extremely careful as how we're going to do it. What we're talking about is the torque. And essentially, let's get down to business. I mean, I'm going to say the torque is the integral of all these differential torques. We're going to sum them all together. And, okay, I mean, let's work that. As we work that, we know that's going to be, we're basically integrating this. We'll figure out, now the integration, of course, guys, goes from 0 to L. Small l is the one that's varying on this. So let's leave that here. I don't know, there's formalities with the mathematics, I guess you could say, but that's not. This is the function. It is varying. I'm doing a torque every single time. There's a small differential pull right here. Right here, there's a small differential pull. Right here, there's another pull. Right here, there's another. There's an infinite number of them, and all of them are, the dF is the same. That's not, the dF is constant. It's very much a differential, but it's constant, more or less. It's the L that you're at. And then you got, from there you're doing the integral. That's really the big thing. Let's see what we got. I just said I and B are constant, so I'm doing this. What you end up getting at the end of the day, you guys, is the torque equals 1/2. Yeah, for real. Crazy. Crazy. Again, I can't emphasize this enough. The differential, the force is the same. Why is the force the same? Because I doesn't vary. B doesn't vary. I doesn't vary, B doesn't vary. That's about it. The torque is different because you have a different location. The differential element of force, depending what your DL is, let's keep the DL the same, something very, very small. It's going to be a very, very small DF, but it's more or less constant. What varies is the torque because you are pulling from a different place. You're pulling from a different place. The lever arm gets longer and longer as you proceed in the integration here. So I got this. Now what? The moment of inertia for this long, thin rod is 1/3 ml squared. It's the moment of inertia. So I gotta, let's write it carefully, I guess you could say. Right? Because we're used to I being one thing, you know. So moment of inertia, I sub m for moment of inertia, is 1/3 ml squared. And those of you guys who had me before, know that we can derive that kind of stuff. Not necessarily easy, but not, you know, it's very doable. Gotta talk to you some more. Isn't torque equals to I moment of inertia? No, we never used that little m there, but we never had I written in another way too, talking about current, right? Moment of inertia times alpha. Wait a minute. Torque equals torque. This is torque. This is torque. Torque equals torque. Moment of inertia. Equals. Forgive me here. I have the alpha there. That's the angular acceleration. This is the thing we're trying to find, guys. Torque equals torque, you got it. The rest is, the rest is what it is. Put all the numbers in there you got to put in there and figure out what the heck is going on here. I'm going to multiply by 3. I'm going to multiply by 3 on each side. Here's the real crazy thing. The L squared is canceled. It's kind of crazy in its own right, isn't it? I mean, look at that. You look at it and say, okay, let's multiply. Let's multiply by 3 on each side. Divide by m, and divide by L squared. Actually. Divide by L squared. Here's I. Here's B. Divide by capital M. So we divide it by L squared on each side, and yeah, the L squared's canceled. We've got this right here. 3 halves is 1.5. This is 12. 3 halves times 12 is 18. Times 2 is 36. Divided by 0.5 is 72. 72 radians per second per second. It's a wonderful problem. It really is. It's got a lot to it. There's some really good problems they have in this book. Okay, that's 72. Let's go to the last problem from chapter 30. I've already done this in discussion. The discussion wasn't too well attended, but I think a lot of people know how to do it. So let me go to it. Let's run through it. Got some great problems here, guys. Hopefully I picked some good ones for you. You've got all of this. You've got all of this online for you, okay? And again, the circumstances, as we make this video, the circumstances under which we're writing this tells us that we gotta utilize what we have in front of us. I think most people, give me 1 second here, guys. I think most people have been utilizing the resources available to them, and I think they're comfortable with it. I've never, I told you from day one, I wasn't going to grade people on attendance. I mean, in some future semester, possibly I'll go in that direction, but I say my big thing was I want to see you guys do well. Okay, so I provide a lot of stuff for you. The course you could do this entire course as an independent study. I purposely designed it to be that way. I had no idea that the circumstances were going to be what they were. So now so that's actually what we're doing at this point. So at least in the foreseeable future. So let's stay with it. We're going to try to get through this stuff, you guys. All right, for 72. Forgive me, 92 rather. The way this is written, I mean, there's a lot of ways to write this. It's a bit confusing how I think in the solutions themselves, they end up using J. Whereas J, we're used to, it's associated with the current density, and the current density usually the association with something perpendicular, the current hitting perpendicular to a cross-sectional area. In this particular instance, we're not going to use it that way. The current and the area are kind of, for lack of a better way, they're kind of collinear, coplanar with one another. The current is going in the same plane. The current's going in the same plane as the sheet of metal that is present on this particular problem. So, it's okay. The big thing is, as long as we can do the mathematics correctly, the semantics aren't going to be too much of a big deal, I don't think. All right, based on what we've already said before, you guys, looking at 92, let's read it and actually go for it. Let me actually erase this first, and we'll take it from there.
If you can stay on one side when you're doing this, I have to go grab the power cord.
Okay, what do you want me to say?
Just if you can stay in, like, from this half of the board over.
From here to there?
Yeah.
Okay, no problem. Thanks, man. Are we are we taped right now? Are we being taped right now?
Yeah, we're being taped right now.
Okay, but you're going to just edit it too, right?
Theoretically, yes. We'll
Okay.
find out if I can manage it.
No problem. Don't worry about it. We've got nothing to hide, right?
Yeah.
All right, guys. As my colleague steps outside a little bit to take care of some stuff, let me keep talking. Let me set up some stuff. Let me read out the problem to you for 92. It's a great problem. And okay. For problem 92, you guys, again, chapter 30. Problem 92, a long straight wire carrying a current of 2 amps is placed in the plane of a conducting strip of width 8 centimeters, and the strip carries a current of 4 amps. The distance from the wire to the near edge of the strip is 4 centimeters. Calculate the attractive force per unit length between the wire and the strip. Okay. Let's write that out and see where we're at. All right, for 92, you guys. Okay, sounds good. For 92, you guys, we've got the long straight wire, 2 amp current going this way. We've got let's see what we got here, actually. Got this. It's not going to be the greatest drawing in the world, you guys, but here we go. So we got this. And we got 4 amps total. Uniformly distributed throughout this sheet, theoretically. So, all right, so we got the 4 amps here, all uniformly distributed throughout the sheet. We got this right here. We got this right here. I think they're telling us this is 8 centimeters. And this is 4 centimeters. Okay. Slowly but surely running out of chalk here. That's a good sign, I guess. So that's it. I mean, bottom line is calculate the attractive force per unit length between the wire and the strip. There's a lot here. I mean, you can say a lot. we can actually find what, you know, we know there's a lot to be said. I think the last time I'd done this a little bit differently, but not too much differently. All right, here's the big thing. We got this right here. You got the current there. You got the current there. They're going in the same direction. There's going to be an attractive force. We know that, well, we know a lot. I mean, we know this. We can say that if you're talking about a long wire, you guys, a long wire, this is kind of the fascinating part about this whole problem. To make this thing happen, we're saying that the current, and we're not passing any kind of judgment of how realistic this is or how realistic it's not. We're just saying there's current flowing through here. It is evenly distributed throughout the sheet. The sheet is very long. The wire is very long. The sheet is very long. The sheet has this width to it, and you know the current's uniformly distributed throughout it as it goes upward. There's current everywhere. There's current everywhere on the sheet, firing straight up, just like there's current here. Basically, if I take a small piece of this, I mean, if I took a piece of this right here, a small piece. If it's not small enough for you, I'll make a smaller piece than that. If I take another small piece here, and another small piece here, etc., etc. If these aren't small, you know what? These aren't very small, but that's all right. I can break this. I can make that one 1/10 the size of what it is now. Also that one 1/10 the size. Also that one 1/10 the size. Now I got 30 strips here, not 3, 30 of them. I can make it 1/100th the size. 1/100th the size, 1/100th the size. Now I got 300 of them here. I can make them as small as I want. Basically, I'm going to make a very, very, very large number. I'm going to make a very, 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 very large number of long straight wires all put together that compose that sheet. All these very, very thin strips are thin wires. All those thin wires together are the composition of this long strip. So I'm making these into an infinite number of wires going this way, and I'm trying to play some games with it. Well, okay. Do you remember, you said, magnitude of the B field or whatever, you want to say magnitude of the B field equals B is going to be mu 0 times I over 2 pi r. And great, so what? And then you say, okay, yeah, well, that's pretty important because if I want to talk about, and remember, that right there was born from this. This really has some fascinating applications. That's got some fascinating applications. It gets us to here. Okay, great, so what? What's the big deal? Well, all the stuff's going up this way. The B field that this guy creates is your thumb this way, B field this way. Bam, bam, bam. The B goes into here. The B goes into here, hits it perpendicular. The I goes upward. The B is this way. IL cross B. The B goes this way, so the B goes into the board. I goes up, B into the board. IL cross B. So we said the B goes in here, bam, B into the board. So the IL this way, IL cross B, bam, attractive force. That's the attractive force that's going to be happening everywhere there. Oh yeah, it happens to be a 90-degree angle. The B field is perpendicular to the current, to IDL, to IL. Let's say IL for now. Later on we're going to say IDL. We can say a lot of stuff. But for the IL that's present, the IL and the B, they're perpendicular to each other. That means it's ILB sine theta. Theta is 90 degrees. ILB sine 90 degrees is just ILB. F is equal to ILB. Yeah, well, each one of those is a different, now, each one of these guys, this is the guy associated with way over there on the left-hand side. We'll call him I1. And each one of those miniature currents is I2. So if you put it, or even if it wasn't, I mean, if it was just two wires, let's not even worry about these small wires right now. Let's worry about like a big wire here, a big wire there. How would you do it? It would be ILB. Yeah, but what is ILB? That's the thing. IL cross B. It's this guy's I cross the B that this guy created. This guy creates a B. Bam, right in there. The I is here. The other I is here. This is the I2. This is the I1. The I1 creates a B field, bam, into here. I2L cross B, attractive force. So there's the I2, and there's the I1. This guy's associated with the I1. This guy's associated with the I2. So it's I2 mu 0 I1 so what do we got? We got mu 0 I1 I2 L over 2 pi r. And that's the thing. I wanted to kind of, I thought we needed to kind of look at that, get a good look at it. So we know this. We know this, you guys. If we know this, what else do you want to say? Well, here's where you got to be very, very careful. Okay, this is kind of the way we're going to go to get this under control. They say a couple things that we need to say as well, I guess you could say. Let's figure out how much current is in each one of these guys. Is in this guy, is in this guy, is in that guy. Now remember, I can make these as thin as I want, so you got to really watch it here. Tell you what, we've got a whole lot of stuff written down there. What do you say you take and say, okay, let's say J is the current density. I'm not going to associate it with a vector at this point because the amount of current that's in here is spread out over here, and so it's not going into a cross-sectional area, it's on a particular cross-sectional area, and I can still play that game, I guess you'd say. So I'll tell you what I'm going to do. I'm going to say that J is equal to I over A. And now we got to be careful. We're going to use MKS system of units and everything else. I is equal to I. That's the total current, you guys. That's 4 amps. That's the I I'm dealing with right now. That's the I I'm dealing with. That's everybody. That's 4 amps all the way across here. Okay. So what? Not a big deal that way. Well, I'll tell you what I'm going to do. If this is 8 centimeters, the 8 centimeters is of course going to be equal to 0.08 meters. And we want to stay MKS system here. We're using amps, we got to use meters, the whole thing's probably the best way to go. We can say that there is a length of wire from here to here. Now the sheet is very long, guys. The sheet goes through the roof. The sheet goes beyond the basement, and to the center of the earth, so to speak. So the sheet is very, very long. But we're going to say we're going to just take a cross-sectional look at it. We'll say if that's L, and that's 8 centimeters, that is, 0.08 meters, if this is the width and that's the height, if this is the width and that's the height, or this is the width and that's the length, length times width is going to be equal to the area. Tell you what I'm going to do. The amount of current that's present is 0.08 meters times L. That's the current per area in that particular area, so to speak. Now we can talk. I mean, we can say a lot. I mean, the big connection here You'll see this in a second. The amount of current that's present per area like that, huh? All right. Well, what do you say you call this guy 4? 'Cause it's 4 amps. The sheet's got 4 amps on it. Then you got this. Man, let me kick this thing around a little bit, I guess you could say. At the end of the day, this is, do the math here, guys, it comes out to here. It says, you gotta be careful now. You gotta be really careful. That's J. And, at least for our purposes, maybe it's not, you know, there's probably more formalities associated with it, but for right now, let's just look at it that way. Okay, you might want to say that. So what? What do you want to say about it? Well, we can say that the amount of current that's going to occur is, you know, there's a number of ways to go here, guys. You can say, okay, this is it. Then you say, okay, there's a DI that's going to be equal to, see, there's, we got to figure, let me try to help you, or at least try to make this make a little bit of sense here. If I go 0.08 times L, I got everything here. If you just truncate this, and that's all that current that's there. How much current is in this little piece? Well, whatever proportion of this there is. I mean, I could just say it's, we could say this is associated, this is current per area, and if this is a differential amount of area, we can basically say, I'm trying to think of a good way to actually say this. If you took, I'm going to go off script a little bit on this one, guys, if I could for you. If we said that there were 4 amps of current for the area that's present, that's 4 amps of area. That's 4 amps of current for the area that's present. If I multiplied it by dA, in other words, 4 amps of current for amount of area A. If I multiply it by dA, it's basically telling you something like this. It's saying, again, going a little bit off script here, guys, when we do this. This is dA over A. In other words, it's probably the best way I could have done it. I didn't really write it like this in the notes. I sort of strongly implied it, but I think it was a little bit too, it was definitely, in my opinion, too ambiguous. If this is all 4 amps, you guys, how many amps are here if this is 1,000th? If this strip right here, if this strip right here, or this strip, which is the same size, if this strip one right here is 1,000th the area, how much current is going through here? 1,000th of 4 amps. So that's kind of where this is where it's coming from. So you could say, okay, how would you want to do this? You could take the 4. You could take the area, which is 0.08. That's the width times the length. That's the width times the length. And the other one, the dA, is dx times L. The L don't mean a whole lot. You can take them out like that, and then you can say, wait a minute, what's 4 divided by 0.08? Well, when you actually do it, it's going to be 50.